I'll start with a fairly simple question. What actually is climate? Do you have an idea or definition at hand? Yeah?
It is like a period of time, like 30 years or something, or like a bigger one time, and what happens in this time. So if there's a warming of the earth, or is there colder periods, and that's climate, I think.
Yeah, that goes in the right direction. So maybe if I ask you a question, for example, let's say next Wednesday, tomorrow, what temperature will we have, more or less? Do you know by chance, or would you know how to find it out? Yeah? Where would you look that up?
Google.
Okay, yeah. And for, let's say, the Wednesday next week, would you still be able to get that information?
Not accurately.
As we go further in future, it's less predictable.
Yeah.
So that's what it's physics. I mean,
Yeah.
you can predict. Like
That's true. So that's the weather
so
forecast
tomorrow
you're
will be
looking
more
at in the
similar
weather
to today.
forecast.
Yeah, but we cannot predict what's going to be next 10 days or even 100 days.
So if I ask you what clothes to bring for Wednesday in January, would you be able to tell me something about it? No idea at all? Or
Yeah.
so should I come in
Yes.
shorts or should I come?
Yeah.
Some idea.
Yeah, but that's not the weather forecast you're thinking about then.
There were the patterns, right, which are repeated over time that become the climate. Right?
Yeah, so that's actually exactly the big difference between weather and climate. You can only know what weather we will get in January because you've experienced that, and then there are people who maybe are here in Heidelberg for the first time and they don't necessarily know that. But yeah, the big difference is that weather is actually the current state of the atmosphere, and then you can look at different variables, so rainfall, wind speed, temperature obviously, also the amount of solar radiation hitting the Earth. That's the variables we're looking at, and weather is the current state, whereas, as you already correctly said, climate is sort of an average weather over a really long period of time. So the typical period is really 30 years. The World Meteorological Organization is using 30 years. If you really look back in time for the planet, you can also look at even longer time periods. But it's a statistical description of the average state of the atmosphere. So what is climate change? As we said, it's a statistical description, so we have a mean and the variance around the mean, and climate change now is a sustained change in this statistical description. So either the mean changes, for example, if you look at temperature here, the whole distribution shifts towards warmer temperatures, so we will get more extremes in terms of hot weather and less in cold. But climate change can also be another change of this statistical value. You can, for example, also change the variance without necessarily changing the mean, which for the example of temperature again would mean that there are more extremes, both more hot days and cold days. And this has to happen really for a sustained period of time in order to change the statistics of this 30 years period. And that's what we're actually observing. For example, here this is a combined data set of surface temperatures, both from the ocean and land surface temperatures. And you have the yearly averages, and the different colors are different data sets, which basically show more or less the same thing. So this is the yearly averages of the temperature, and if you look at this in decadal averages, especially here for the, let's say, last 30 or 40 years, you see a clear increase in this average global temperature. So that's climate change, whereas here there is probably a combination of the internal variability of the system, which you can also see here from year to year, and a climate change aspect to this change. Okay, so I've talked about temperature a lot, but actually the climate system is described with a lot, or with a number of different variables. So there are different ways where you can actually see and measure the climate, and from this whole set of, and that's already a selection, but from this whole set of variables that describe the climate system, 7 have been selected for both communication reasons but also for measurement reasons, so things that are easily and reliably to measure that really characterize the current state of the climate system. So there is the temperature we've already talked about, so the temperature over land is one of these variables. Then there are variables mostly linked to the ocean, so the sea level, the heat content in the ocean, and also the acidity of the ocean. Then there is, so there's the cryosphere, so all areas on the globe that contain frozen water, and there an important variable that describes the system is the volume of the glaciers, and then again on the oceans the surface area of sea ice. And the last essential climate variable, as they are called, is the concentration of atmospheric CO2 in the atmosphere. What we are trying to do now, or what I'm trying to do or explain to you now, is how actually this climate change comes about. What is really behind it? And in order to understand that, and because most of the processes on Earth in the end have to do something with energy, and mostly with the solar energy arriving at the Earth, we will start describing the climate system and start with a really simple model. So we'll just look at the Sun and the Earth in space and try to understand the energy budget of this fairly simple system. Before we do that, there are like two physical properties of all matter that we will need later, so I'll quickly remind you of that. So all matter that has a temperature that is above absolute zero emits energy in the form of electromagnetic radiation. And the wavelength distribution of this emitted energy, so the colors of the light, you could say, that depends on the temperature of the body. So for example, you see these different curves, and they all are the distribution of wavelengths linked to a certain temperature. This, for example, is 5,000 Kelvin, so 5,273 degrees Celsius. And there you see that the electromagnetic radiation that is emitted, the maximum is actually in the range we call the visible wavelength range. So what we as humans are used to and what we've adapted to, because this is close to the temperature of the Sun. So this is more or less the solar spectrum arriving on Earth. And the colder the temperature of the body that emits the energy gets, the more this distribution shifts towards the red. And this is an example where you can more or less also see that. This is a metal rod, and where it's really hot, it seems more or less white, and where it gets colder, it first looks red, and then you can't really see an emission, and that's when this distribution is really in the infrared, which we can't see anymore. So that's one thing to keep in mind. The temperature determines which distribution of energy is emitted by the body, and the temperature also determines the overall amount of energy that is emitted. So if you compare a square meter of ice to a square meter of boiling water, the overall amount, over all the different wavelengths where this matter emits, is much higher for the boiling water than for the ice. And this is proportional to the temperature, again, of the body to the power of 4. So these are the two basic properties we now need to understand our model. Yeah, this is again the distribution of the two bodies in the model we are looking at. Again, the Sun with the visible spectral range we have here, and because the Earth is much colder, the average temperature of the Earth is 15 degrees Celsius. So the emission of the Earth is really here in the infrared spectral range. So if you put that into our model, first starting with the emission of the Sun, you have the sunlight going through space, hitting the Earth. A fraction of that sunlight is reflected on the surface of the Earth, and the rest is absorbed by this. In the simple model, just a sphere of, let's say, rock that is painted like here on the slide. And the fact that there are clouds and continents, that leads to this reflection of a fraction of the radiation. And then there's the emission of the Earth itself, and this is in the infrared, due to the lower temperature of the Earth. If we now look at this really simple model and imagining the Earth just as a piece of rock in space, then we would end up with an average temperature of minus 18 degrees Celsius. So clearly in this model something is missing. Do you have an idea what that could be? Yeah.
The atmosphere.
The atmosphere, exactly. So we will now need to refine the model a little bit to really get to the average temperatures we are having on the planet. And for that we now look at the Earth a bit closer, and we start again with the incoming solar radiation. So we have all the solar radiation arriving at the top of the atmosphere, and then, as we know, there are clouds, so part of this radiation is reflected on the clouds and goes back into space. The rest hits the surface, and also on the surface there's some reflectivity, so also a portion of the visible wavelength range is emitted back to space. But actually most of the solar radiation is absorbed by the ground and heats that up. And that's actually what we can see if we look at Earth from space. So this is the visible spectral range in a black and white image, but what you can see is you have the continent and the land masses, so that's light reflected from the surface, but you also, where you have clouds, you have just these white areas, so there the light is reflected from the clouds. Okay, so then we look at the infrared spectral range, and there we have the emission of the surface due to its own temperature. And now the atmosphere really comes into play, because our atmosphere contains molecules that, due to their molecular structure, absorb most of this infrared radiation. So the radiation is emitted into the atmosphere but doesn't really get through. There's only a really small portion that makes it from the surface into space. Most of it is absorbed by the molecules in the atmosphere, and only if you go to a certain altitude, the atmosphere becomes thin enough for the infrared radiation to escape to space. So what happens is the radiation is emitted from the surface, is absorbed, and now the atmosphere itself is also matter that emits electromagnetic radiation, and that in all directions. So it emits also radiation towards space, but only at a certain altitude this radiation can actually escape into space and then is gone from the system. And this is what you can see here on this, again, black and white image. That's really the same point in time, but you can see that you don't see the surface, you don't see Africa here, you only see structures that are in the atmosphere, so at an altitude higher than the surface. And as you probably all know, the temperature in the atmosphere is lower than on the surface. If you've been on a plane and looked at your thermometer or the little screen where they show you the outside temperature, or if you've climbed a mountain, you know that the temperature is lower in high altitudes. And then we need to remember the fact that the temperature determines how much energy is emitted. So if you compare what is emitted from the surface and what is emitted from this altitude where it actually can escape into space, this is much lower. And the missing bit of the energy that isn't escaping into space is obviously radiated back to the surface, and that's what is heating up the surface. That's what is leading to this average temperature of 15 degrees Celsius, and that's the greenhouse effect. And this is actually really important because, as you all know, at minus 18 degrees we wouldn't have life on the planet, at least not as we know it. So this natural greenhouse effect, which is mostly due to water vapor in the atmosphere, but also natural CO2, is really an important prerequisite for the Earth as we know it. So this is the main bit of the energy budget. Then just to be for completeness, there's also an emission of energy from the surface into the atmosphere via sensible heat. So that's the heat you can feel. And there's also the transport of latent heat. So that's when you have water vapor and the air rises, and at some point you form rain, and this phase transition also releases energy in the atmosphere. But that's just to have the complete picture. The important bit is actually this dual system of the visible wavelength range, where our atmosphere is mostly transparent, and the infrared, where it doesn't get through and only gets into space from a certain altitude. Okay, maybe I'll make a quick break here if you have questions on that. Yeah?
Could you go back to the...
Yeah.
So comparing the first and the second part, so the yellow arrows and the orange ones,
Yeah.
like what's the difference between them in like in terms of orders of magnitude? I suppose the yellow ones are much larger number, like in terms of total energy.
Well, if we look at the system in equilibrium, you only get an equilibrium in terms of the energy if the amount of energy going out is exactly the amount of energy that is coming into the system. So if we are not in a moment like now where we have climate change, the amount is actually exactly the same. The thing that, because you're right, the sun, as it's much hotter, emits more energy. Then you have to factor in the distance from the sun, so it emits in all directions, so we only get a fraction because of our distance. And then you also have to think about the fact that, so from the sun at the distance of the Earth, we get about 1,360 watts per square meter of energy. But this only hits a circle, circle more or less. So and the Earth constantly turns through this. So on average, we get 341 watts per square meter because, we have a surface, the surface of a sphere, whereas the light just hits the
plus the
cross
energy
section,
which is naturally released from Earth.
Yeah, so there's a really small amount of energy coming actually from the soil, from the surface. That's due to radioactive decay in the rock, and also especially where you have volcanic activity, there's some heat coming up. But that's compared to the amount of energy arriving from the sun. That's 1 to 2%, depending on where you are on Earth. But that's sort of the order of magnitude.
So like the 99% is actually the one coming from the sun.
Yeah.
And the greenhouse effect applies to both types, because you say they are in different wavelengths.
Yeah, so the greenhouse effect works because it only blocks in the infrared.
Mm-hmm.
There's very little absorption of the visible radiation coming from the sun. I mean, you can see the stars. You couldn't see the stars if your eyes were adapted to the infrared, because then you would have the water vapor, for example, in the atmosphere. And so seen from the surface, like looking up in the infrared, the atmosphere is transparent, and only when you only have a certain amount of atmosphere left above you, it becomes transparent. And from there, the energy can escape into space. That's the basic mechanism.
So the main problem of the greenhouse effect is that it's basically capturing back this 1 or 2% that Earth should be emitting naturally.
Well, I mean, in general, the greenhouse effect isn't a problem. It's rather really important, but we will come to the changes that we have introduced. Or that's really what I'm going to talk about now. So the ways how we can influence this energy balance in the system. In order to illustrate that, I sort of summed up the incoming amount of energy and the outgoing amount of energy, which is made up of the visible and the infrared part that is going out. And so that gives you the overview of the system. So we're starting with the system in balance, and now there are basically two main ways to influence the energy balance. One is on this visible side of things, and the other is on the infrared side of things. And we will now start on the visible side. And for example, if we look at this white area, we can increase the reflectivity of the surface of the Earth. One example how that happens would be if we have, for example, a dark forest, and now we've cut it down and there's a desert. That's much brighter seen from space, so there's more reflectivity. And what this does is that the reflection at the surface of the Earth is increased. So we have an imbalance in the system, and there's more energy going out of the system than coming in. And on the other, you can think of the exact same thing happening, but in the other direction. You can also make the surface darker. For example, now there are more trees in the tundra area of for example, Russia growing, and they are darker than the grass that used to be there, so you have more absorption, and that would lead to more energy coming into the system than going out. So there's an imbalance. And then the other way, as I said, is here in the infrared spectral region. And now we are coming to the effect that we, as humans, have with the emission of additional greenhouse gases. So we emit this CO2, for example, and what this does is that it makes, in terms of the optical properties of the atmosphere, it makes it thicker. So the altitude where the atmosphere is actually transparent is moved up. You still can only emit the energy to space from an altitude where you have a certain amount of atmosphere above you, but this altitude is now moved up. And now the temperature still decreases in the atmosphere, so at this new altitude of transparency, the temperature is lower than at the altitude where we were before. So the overall amount that is emitted by the atmosphere from up here is lower. And that's what leads to this imbalance in this case. So there's not as much infrared radiation emitted with more greenhouse gases in the atmosphere. Is that more or less clear? Yeah. Okay. So yeah, these are the two basic mechanisms. Now if we want to figure out what we as humans are actually doing in total, we have to look at all the different effects that we are having on the atmosphere and also on the property or the reflectivity properties of the surface. So this is fairly complicated. I won't go into all the details, but one way we can influence the optical properties of the atmosphere are gas emissions. And there you can, again, distinguish between gases like the CO2 we've already talked about, which is basically just emitted into the atmosphere and now it's there and is moving up this altitude from where the radiation is emitted. You also can emit other gases which, depending on their chemical properties, maybe first have to react to form CO2, for example, and then act on the radiation budget. And then if you look at others, for example, the halocarbons, they have a double effect. They themselves are greenhouse gases like CO2, but they destroy ozone, which is also a greenhouse gas, so that gives you a negative impact on the energy balance. And in order to figure out the overall impact, you need to determine these different influences on the radiative forcing. So that's what this impact on the energy balance is called. That's the radiative forcing. And yeah, you have to figure out if it has a positive or negative impact. Then here, this is the impact that particles and also gases that can form particles are having. And that also depends. If you have, for example, soot from burning stuff that's really black, that absorbs a lot of energy, that has a positive radiative forcing. But you can also have other particles that more or less act like a sunscreen for the planet, and they reflect more energy than they actually absorb, so they have a negative radiative forcing. And then that's also part of the particles. The cloud changes, or the optical properties of the cloud change in relation to the amount of different particles in the atmosphere. And then the last bit we already talked about was the albedo change, so that's the change of the reflectivity of the surface. And that, at the moment at least, has an overall, like a slightly negative radiative forcing, so it balances off a little bit the impact of the greenhouse gases, but if you look at the different bars, you see that the positive impact of the CO2, the positive radiative forcing is much larger. Okay, so without talking much more about this, but to give you an understanding or feeling for how we come up with these numbers, I would like to talk about the radiative forcing of CO2 and how this value is actually determined. And for that, we maybe look again in detail at what is actually shown here. So we have this additional radiative forcing relative to 1750. So that's when we think the Industrial Revolution started. And then this is so this is the anthropogenic impact on the radiative forcing relative to this year, and what we, in order to determine this number, the 1.7 watts per square meter, So what we need to determine this number, first of all, is to know how much CO2 we have in the atmosphere right now, how much CO2 we had in the atmosphere at 1750, if the CO2 is really from anthropogenic sources, and then what this does in terms of the energy balance in the system. And this radiative forcing of CO2 to determine the number, for example, that is linked to a doubling of CO2 in the atmosphere, that's actually fairly easy to determine. So, I mean, there's an error bar, but about that value we are quite confident. What we need to do now in order to end up or to get this 1.7 watts per square meter is, as I said, first of all, look at the CO2 concentrations in the atmosphere right now. And this is the longest time series of really direct measurements of CO2 in the atmosphere. It starts in the late 1950s. That was done at Hawaii. That's the really famous Keeling curve. And you can see this increase of CO2. The red curve, that's actually what is happening throughout the year. So you have the biological activity that takes up CO2 and then during the winter releases CO2. That's what leads to this, this up and down. But you can see that we only have direct observations until back until the 1960s, more or less. So in order to determine this effect relative to 1750, we have to go back in time. And one important tool for this are the climate archives. And in this case, for example, we can look at these ice cores. So you drill into a glacier, for example, in Antarctica or in Greenland. And what you can see here on the photo is that in this ice there are these little bubbles. And in these bubbles we have the composition of the atmosphere back in time. We now need to determine which depth corresponds to which point in time. But basically, in the bubbles, you directly get the CO2 because it's a fairly stable molecule. You can directly measure the CO2 concentration back in time. And with these ice cores, we can go back to 800,000 years before today. They are now looking for spots to get to 1 million years before today, but that's more or less the range we can cover with the ice cores. And here you can see the CO2 concentration in the atmosphere. This is where we are 2017. And then as you go back, you see this up and down, which corresponds, so the points in time where the CO2 concentration was high was a warm period, interglacial, and when it was really low was an ice age. And in comparison, where we are today, this is much, much higher than even the highest concentration of CO2 back in time during one of these warm periods. So from there we don't even need the entire ice core to determine what concentration we had in 1750, but that's where we get this value from. And then we need to really link the concentration in the atmosphere to our activities. And one way to do that is like a bottom-up approach. So we more or less know how much fossil fuels we used throughout history. And this is coal, oil, and gas, and then there's also a bit CO2 linked to the production of cement. But that's basically what we emitted. I mean, the chemistry of burning stuff is fairly easy to use for this estimate. So that's what we've emitted into the atmosphere. And then, in addition to the fossil fuels, we also changed the surface of the Earth, and that's plotted here. So this brownish curve is the emission of CO2 due to changing land use. For example, cutting down a forest emits CO2, and that has been fairly high throughout this time period we're looking at right now. And only in the recent years the emission of CO2 from fossil fuels has really taken over. So if you compare this time period 1750 to 1970, it was more or less 50% from the fossil fuels and the rest from land use change, and since 1970 this fossil fuel impact has really increased. Okay, so with this we have an idea of what CO2 levels we would expect in the atmosphere. If we compare that to the measurements, we actually find that not all the CO2 we've emitted ends up in the atmosphere. So there's a part of the CO2 that gets into the ocean, so first just dissolved in the ocean and then even chemically dissolved in the ocean, and only 50% stays in the atmosphere, and the rest we think is taken up by the biosphere. So trees growing a bit better if there's more CO2 around. But as you can see from these huge variations here, there's still a lot of uncertainty about the role of the biosphere in this regime of increasing CO2. But I mean, that's what we observe, that's also what we measure, so the rest has to end up in the biosphere. Okay. So yeah, that was just to give you an idea of what is behind these different radiative forcing bars. Okay, so far we've only talked about this energy balance and the watts per square meter that are arriving additionally to the normal equilibrium. What we would like to do now is to get back to this set of initial variables that really characterize the climate system. And before we do that, maybe another quick break and time for questions, if there are any at the moment. Yeah.
So how homogeneous is the atmosphere in terms of the gases? So let's say the CO2 is measured at one particular location.
Yeah.
Is this a reflection of the total CO2 that is present in the atmosphere, or just a reflection of a particular location?
That depends a little bit on the gas. So for CO2, it's, I mean, if I go back to this overview, for CO2 it's fairly easy because it's a very stable molecule. So I think the average lifetime of a single molecule in the atmosphere is 100 years. And the mixing time of the entire atmosphere is about 1 year. So, but at the same time, as you saw, that there's this big variation throughout the year, and which is due to the biosphere mainly, taking up CO2, also releasing CO2, and that, for example, leads to a difference between the two hemispheres. You have more variations on the northern hemisphere because there are more land masses and more biosphere taking up and releasing CO2, and much less on the southern hemisphere. So there are some differences, but this is, and because of the still the sort of unknown role of the biosphere, there are some differences, but I would say the differences between two different locations, they stay pretty stable throughout an increase. But yeah, there are slight differences, and that's, for example, why we have background stations. For example, in Antarctica, that is really far away from anything that grows and also releases CO2. So I think the black curve that was in there was actually from a background station that has less impact of the biosphere, and then the red one was from Hawaii, which with more impact. So there are differences, but in general, CO2 is well mixed. And it also doesn't change where you emit the CO2 in terms of the radiative forcing that it will have in the end. For other gases which are short-lived, there can be regional gradients, I would say. Yeah. Are there other questions? Okay, so I go back to this slide. So from this radiative forcing, which is a good measure to describe the energy balance of the system, but not a really good measure to actually estimate the impacts of this climate change. Yeah, we now want to link our variables from the beginning to the radiative forcing. Okay, so and this is really much more difficult than just coming up with the radiative forcing, and that's due to feedbacks in the system. So, and in order to explain the feedbacks, we now start with a system where we've emitted CO2, and this altitude has moved up, so we are emitting less of the infrared radiation into space. We have this imbalance. The first reaction of the system now is that it warms up. And what this warming up does is that at the altitude where we actually release the infrared radiation to space, the temperature rises until the amount that is linked to this particular temperature equals the amount that previously was emitted from the low altitude. So we emit the CO2, this leads to a warming, and it warms until the altitude from where this infrared escapes into space is high enough to really balance the system again. But this warming has then secondary effects, and these are the feedbacks. So one of the effects, for example, is that sea ice surfaces, or also the ice packs on the continents, like on Greenland and Antarctica, they disappear. And they, since they are very white, they reflect a lot of energy into space. With less of sea ice, for example, we have more absorption. And that's again leading to an imbalance in the energy budget. Another effect that the emission of CO2, for example, has is that when the atmosphere is warmer, it can hold more water vapor, which is also a greenhouse gas. So the warmer atmosphere leads to more greenhouse gases in the atmosphere, which again moves up this altitude and again leads to an imbalance. So both the disappearance of sea ice and also the increase of water vapor in the atmosphere, they are positive feedbacks. So they increase the effect of the CO2. We can also have negative feedbacks. For example, I said that, for example, trees are growing a bit better when there's more CO2 available. And this obviously lowers the CO2 concentration in the atmosphere slightly, which then leads to the lowering of this altitude to an area where it's warmer, so the amount of infrared radiation emitted to space is higher, and this leads to more emission than incoming energy. But because all these different effects and feedbacks, they are linked, it's really difficult to calculate the amount of warming that is linked to a certain emission of CO2. Now you could say, well, we've seen there have been 4 decades of climate change, can't we just use the observed temperature measurements? We know how much CO2 we had in the atmosphere during that time, can't we link the effect of CO2 on temperature just through these observations? And one big problem is that the system is really slow to react. So right now the oceans still take up a lot of the CO2, they also take up a lot of the energy, and because the mixing time of the ocean is really long, we still haven't reached an equilibrium. So we can't just look at the observations and link them to the CO2 concentrations. And that's why a really important tool that is used in climate sciences are climate models. So these are huge coupled models where you have a grid over the entire globe, including the different compartments of the climate system, so ocean, land, the atmosphere above, and you try to describe all the effects and processes that actually have an impact on this energy balance of the whole system. And with these models, you can do basically two things. One is to attribute what we've already seen, what we've observed, to different effects. So you can run the model, for example, with the assumption that the change we're seeing right now in temperature is just due to natural effects. For example, increased volcanic activity, change in solar radiation. And if you do that, and this is an ensemble of different models, and you see so these are different sets of models, and the black curve is the actual observed temperature increase, and the different colors, that's sort of the uncertainty around the mean of the models. And what you can see here is that for most of the time this kind of works. So there you couldn't really tell if this temperature is really driven by anthropogenic effects or natural effects. But since the 1960s, when we had this temperature increase, you don't really get a good fit between the models and the observed increase. Whereas here on the right side, it's the natural and the human forcing. And there you can see that this temperature increase that has been observed is captured much better by the models. And this is relatively coarse. You can now also look at specific greenhouse gases and try to determine their impact on the warming to get an idea what does how much. That's looking back into time. The other thing you can do is to run the models into the future and determine what temperature you will get based on different scenarios. And what is actually quite surprising, given all these feedbacks and this really complicated and in general non-linear system, is that what you get with these climate models is a more or less linear relationship between the total amount of CO2 emitted into the atmosphere and the temperature increase that will result in 2100. So that's the time horizon for these models. And what you can do with a result like this now is, if you have a target temperature you don't want to cross, you can look up how much CO2 you can still emit. So if we take, for example, the 1.5 degrees, and then we look up our budget that is still left, and we end up at this value of about 420 gigatons of CO2 that we can still emit until we reach 1.5 degrees temperature. And then you can do all sorts of calculations. For example, a really simple one, we had annual emissions of 42 gigatons per year in 2017. That's the budget that is left to stay below 1.5 degree with 66% probability. So as you can see, there's a quite large uncertainty in both directions here. But if you assume a linear decrease starting right now, we have about 20 years left. And then it depends what pathway these reductions will follow. But yeah, that's the order of magnitude in terms of the time we have left if we really want to stay below these 1.5 degrees. Yeah, this is the last point, at least in my part. So that's on these limits. The one that is really on the news right now is the 1.5 degree limit. The other one before was the 2 degree limit. Originally, they actually come from economics. So an economist came up with the 2 degree target because he looked back in time and said, well, we shouldn't deviate too much from what we are familiar with as humans. And that's sort of the idea that is, again, illustrated here. This is now the temperature we had on the planet going back in time. It's a bit complicated because they've cut the plot, but the important bit more or less is here. So if you look at the temperature until 10,000 years before Christ, you see that it only varied about plus minus 1 degree. And looking back into human history, so that's when we came up with agriculture. That's when we had the first complicated civilizations in the Middle East. And so basically, human civilization as we know it has only happened in this period and with this variation of temperature. So that's the basis for this argument for a limit, that we shouldn't really go far away from what we know as humankind. And here on the other hand, you can see the projections of different scenarios. So I think the red one is the business as usual, and there we would end up really well above 5 degrees temperature increase. And the other argument is that, as we've seen, this relationship between temperature increase and CO2 emission was fairly linear, but we know that there are elements in the climate system that can tip, where we can, if we cross a certain threshold, then non-linear effects start to work. So, and this is illustrated a bit here. So far Earth has been moving maybe here between the ice ages and the interglacials in this landscape of sort of stability. If we now deviate by our CO2 emissions from this system landscape, and then at some point cross a threshold that leads to these non-linear effects, then we might not be able to get back to a state that we're used to and that we had before. And examples for this are, for example, the permafrost soil in Siberia. So there's a lot of methane, which is also a greenhouse gas that is stored in there. If we let the Earth warm to a point where this melts, we will get the emission of the methane, and then we can do nothing anymore. We will have continuous emissions even if we really abandon all fossil fuels, and the entire system will continue to warm up. Or another example is in terms of sea level rise. there are the big ice sheets in Antarctica, and some of them they are on rock which is below the current sea level. So if they recede to a point where the water can flow below the ice shield, this increases the melting, and then the entire ice shield more or less is lost and will collapse. I mean, this will take a long time, but that's a sea level rise of a couple of tens of meters locked in, and nothing we can do about it anymore. I mean, we might be able, or some countries might be able to rise their dikes, but that's something, yeah, that is once that has started, and people think that, for example, parts of the ice sheets in Antarctica, they are already unstable in a way that they will recede and continue to recede right now. Then we can't do anything anymore. So this is another argument for staying within a range where we know the system is linear. Okay, so this was my part. Maybe should we have a quick break or time for questions? Yeah.
I have a possibly silly question. So we could try to approach this problem by reflecting more light from the sun, right? So you know what would be the area that you would have like to cover with like a reflective surface to actually reflect enough that we could.
Yeah. So this goes in the direction of what is called climate engineering, and the climate engineering can be separated in the, again, like in this energy balance system, in managing the incoming solar radiation. So I don't know the surface you would actually need. I think it's in the order of the Sahara at least to have an impact. So there are also ideas of painting roofs white and stuff like this. But if you calculate that through, it's most of the ideas are uneconomical. So another idea that is, I think, where a couple of scientists are a bit more serious about is to simulate volcanic eruptions. So if you have a really big volcanic eruption that emits a lot of sulfur into the upper atmosphere, this cools the planet. And that has been, for example, the last big eruption was 91, the Pinatubo eruption, and there the temperature the following year dropped by 0.5 degree. So if we continuously get sulfur to the stratosphere, we could offset the warming we are producing with CO2. There are a lot of big problems with that, because once we try to fiddle around with the temperature knob on our climate system, first of all, a political question like what is the right temperature? And I think Russia would have a different opinion on that than the small island states in the Pacific. Then, if for some reason the system stopped because we as nations wouldn't agree anymore to do that, the release we have, the increase in temperature we've offset by that would dramatically happen within a couple of years. So that would be even worse than the increase we're seeing right now with CO2. But yeah, there are people thinking about that, and I think putting up the CO2 into the atmosphere, you would probably have to first design planes that are able to do that in a more or less economical way. But in theory, like a big country could probably decide to do that, and then the others, couldn't really do something about it. But it would also have strange consequences. For example, the optical properties of the sky would change, so we wouldn't have blue skies anymore. So, yeah. Other questions? Okay.
So do you guys want a break? Like we have about 18 minutes more slides to go before the game. We can just now go through and go to the game, or we can make a little break, like 5 minutes if someone wants to go to the bathroom. Or who wants a break? Okay. So I'm going to talk about land use change, like just to draw your attention to this topic, because usually all the discussion around climate change is focusing very much on the fossil fuel emissions, and the land use change is one topic that is not that much discussed, but recent models show more and more importance actually of this area, and like recent research is diving a bit deeper into it. So basically, as Jan was already describing, forests, wetlands, peatlands, mangroves, they very efficiently absorb and store CO2. So like one obvious result of the land use change, like deforestation or drainage of the wet areas, is that this CO2 that was stored by the biomass is released back into the atmosphere. Apart from that, also forests and like plants in general, they emit themselves some biogenic organic compounds that can have both positive and negative radiative forcing. For example, they can react with the oxygen, and they can produce this way like more greenhouse gases on the positive radiating forcing, but they can also react with other chemicals in the atmosphere, and they can produce aerosols that Jan was talking about, and this would be like on the negative side. But in total, recent research has shown that these organic compounds, like if as a result of deforestation, their emissions get lower, and this results in warming. So also forests and other biosystems, they have non-radiative forcing. Like for example, plants, they accumulate a lot of water in their roots and the soil, so which results in cooling overall of the surface. The transpiration of the plants can cause building of clouds and rainfall in certain areas, and also forests drive the distribution of air and water. So when you, for example, deforestation can cause in the redistribution of heat, and this can also cause unpredictable effects on, like, this is just to name a few, like in total deforestation, non-radiative forcing of deforestation was shown to also result in warming. So, but I mean, why, like if you look at just this, plot, you have seen it before. So this is like the land use change is here in brown, and these are all fossil fuels. So one first thing to notice is that, like while the fossil fuel emissions started with the industrial era, like the land use change was happening much earlier. Basically, of course it's also human impact, but it started, with the human civilization. And if you just look at this plot, you think, why should I care about land use change? It has so much less effect than this grayish fossil fuels. But it's interesting how actually these numbers are computed. So interestingly, like the emissions caused by the land use change then consist of two components. One component are the emissions resulting from deforestation and drainage, right? So what directly, like if you cut off the trees, if you drain the wetlands, what is emitted into the atmosphere? But then, of course, if you cut off trees, there will be something else growing, like little plants and forest, or like there will be like other processes happening in there, and this will still result in like absorbing carbon. But all these consequences are subtracted from the emissions that are caused by deforestation and drainage. So it's in a way like if we stop deforestation, this will have a double effect, because we will stop emissions that are resulting from releasing carbon into the atmosphere, plus the older forest and their original wetlands and the systems, they will be able to absorb much more than what this small young plants are absorbing that are growing on top. And if you look at this plot, it's like fairly interesting. So these are different pathways of mitigation of CO2 concentration. Like recent models show that the land sector alone can offer up to 37% of CO2 mitigation, at least by 2030. Like this is this line here. And in particular, tropical forests, mangroves, and peatlands, and they can offer up to 23% of total mitigation, up by 2030. This is like really massive. Yeah, but like what do we see happening right now? It's just the opposite. Actually, like especially in the tropics, like you just seen, tropics are so vital, but deforestation is still massively growing. So this is what's been happening in the last years. And if we see tropical deforestation as a country, so it would emit more than the whole European Union. That's what's currently happening. And there are different reasons for deforestation in different areas. So here we are looking at the Brazilian forest, Congo, and Indonesia. So in Brazil, it's mostly pasture. but also like lately forest fires. I guess everybody has heard about this. And in Congo, it's mostly small-scale clearing, and in Indonesia, it's mostly plantations, like oil plantations and the forest fires. So there is this really cool interactive online system called Global Forest Watch. I encourage you to check it out. You can look in the areas you're interested in. It's like real time. And there you can, like, it's a screenshot from there. There you can see where the most deforestation alerts are happening right now. And you can clearly see it's like all the tropical areas. And these are the forest fires, like also right now, real time. Again, have a look, the most affected areas, again, is mostly tropical areas. So this is like quite sad. Any questions on the forests and land use change?
What does the colors mean?
Here?
Yes.
So basically these are just, it's one color, it's just showing where there is active deforestation happening right now. So here it's the same, it's like one color, like one dot is showing where the forests are burning right now.
Black one?
Yeah, I mean, yeah. It's the amount of like forest burning right now.
Not the literal surface.
Huh?
But it's not the literal surface. The surface area that is covered.
Yeah.
Don't the points correspond rather to the amount that's burning?
Well,
But it's not.
I mean, it's kind of like,
Yeah,
they're
they're
all kind
points.
of like dots. I mean, if this map is like super good resolution. You can zoom in, and with a pretty cool resolution, like up to, like a town, you can see where exactly the forests are burning. So this project is amazing, really, Global Forest Watch. I really recommend you check it out. Okay? So yeah, impacts of climate change. When people talk about the impacts of climate change, there's a lot of conversation going on around polar bears and coral reefs and penguins. But this is not what we're going to talk about now. We're going to talk about us humans and how it is affecting us. So there is this really cool study of the University of Manoa, Hawaii, where they took together hundreds of different studies on climate change impact on humans. And they made a really interesting summary, and there is an interactive map that you can play with, where you can see how these different effects in different areas are playing out. And these are the main points of, like the main areas where they detected climate change affecting humans: health, food and water supply, infrastructure, economy, and security. If we look a little bit closer into it, right, so warmer temperatures, extreme heat, drought affects our health, obviously, water supply, agricultural productivity, pollution, forest fires, like very interestingly also water transportation, which is, for example, relevant for Germany. I don't know if you know about, like last summer there was a significant drop of the river level in Germany, and this really disrupted the water transportation, which resulted in higher prices on gasoline. Also, like reduced learning and worker productivity, like it was shown by research that when the higher temperatures are hitting, like people are less productive and more tired, and this has clear economical impacts. Sea level rise, extreme rains, floods. This causes loss of infrastructure and homes, of course, death, injury, but also loss of like water supply and food supply. Ocean acidification and CO2 in the soil, certain commercially important marine animals, fish, they suffer from it, and again we lose agricultural productivity. There are interesting and non-trivial, more complicated effects, like for example with a warmer climate, dirty water, and more rains, the diseases spread, certain diseases spread much more in terms of geographical range, for example, but also season, like how at the time when they are spread, and there are certain infectious diseases that really like these conditions. Loss of homes and infrastructure and resources results in people being displaced, migrating. It results in poverty, but also conflicts and wars. And there are scientific papers showing that it really has this, like climate change is really having this effect. So here we're again looking at an interactive map that you can explore, and this map is showing the vulnerability to climate change of different countries. So it's so-called Notre Dame Global Adaptation Index, which is displayed here. And as you can see, like these greener countries in the northern hemisphere specifically, they are less vulnerable, and those countries that are depicted in red and orange are most vulnerable. And if we look at we compare this image to the emission image, those are the CO2 emissions per capita, 2017. It's really remarkable how you can, you look at those two and you see that they're pretty much complementary, right? Again, the most emissions per capita are produced in the northern hemisphere, right there, and this is the countries that are the least vulnerable. Again, we can look at this picture from a different perspective. These are cumulative emissions from 1751, when the industrialization happened. And again, these dark red countries are those that have produced the most emissions since 1751. And basically, those are the countries that were using cheap energy, mostly coal, to develop, right? And those are the developing countries. So, okay, so let's talk quickly about the proposed solutions on a global level. So they kind of fall into four main categories. One category is about stopping fossil fuel emissions and replacing the fossil fuel energy sources with the renewable energy. Another big sector concerns agricultural and fishing practices, like more sustainable agriculture and fishing-free zones. This is something that can also, like we just discussed, can produce a big effect. Then there are suggestions to directly remove CO2 from the atmosphere. They're ranging from afforestation, for example, planting more trees, to chemical ways of remove the greenhouse gases. And the very important area is the adaptation to rising temperatures, because climate change is real, it is happening, we cannot do anything about it, so we have to have strategies of how to adapt. For example, one very simple idea to build seawalls for the rising sea levels, but also strong proposal is on establishing so-called climate fund so that we have spare money, to mitigate the effects of climate change. And here we come to the Paris Agreement, and everybody heard about it, but I just want to give you an idea what it is actually about, right? I mean, I'm sure everyone has heard about the Paris Agreement, more or less, by now. Okay, so these are the key points of Paris Agreement. First of all, it's about keeping global temperature so-called well below 2 degrees. This is exactly how it is formulated, well below, and try to limit to 1.5 kind of. And achieving carbon neutrality, which means we try not to increase the amount of greenhouse gases in the atmosphere. Every country sets their own goals according to this agreement. So there is no global committee that is watching over the countries or checking if they're actually fulfilling this goal. So you're kind of checking on yourself. And there is a review of the contributions every 5 years. According to the Paris Agreement, countries agreed on setting up a climate fund for the developing countries, which comprises currently around $100 billion per year. Then there are discussions on adaptation strategy, how to reduce the vulnerability, and on education and raising awareness. So this is the map that is showing countries that have entered Paris Agreement up to now. So there are 179 different parties, European Union is one party, and these countries are responsible for 89% of all emissions. So here you see the United States in yellow, because United States is planning to exit the agreement, which is going to cause lots of problems, but yeah, up to now they are still in. And those are these pledges or promises that different countries have submitted. And you can also see in blue, those are the countries that have submitted some promises, and the gray are those that didn't submit anything. And so let's say they are in the agreement, but they are not have any strategy or plan, about what to do. So here we're looking at Germany. Germany is a part of the European Union bloc, and it has set a goal of 40% emission reduction by 2020. Unfortunately, Germany is missing this goal. So this is where Germany is right now. So this is the target. And the current projections are showing that, this is the realistic forecast kind of for Germany. So it's clearly missing the goals. And if we look at the just renewable energy consumption across Europe, so here you have plots showing different countries. So the yellow ones are those that reached the gross final energy consumption via renewable energy, and the red ones are those that miss this goal. And again, we see Germany, where is it? Here. It's also missing the goal of introducing renewable energy. So those are different scenarios that we are facing now. So that Jan was already explaining. So this is the scenario where the so-called business as usual, we do nothing, and we can be pretty clear we will be above, like by 2100 we will be above 4 degrees warming. So the current policies that countries are implementing are here. So it kind of ensures us that if it will be going on like it is going on right now, including United States being in the agreement. So we will have above 3 degrees warming. So those are the pledges that countries have submitted but are not fulfilling currently, like they actually want to end up. So you see, it's not enough happening. And it's a real problem. So that's why people are protesting. So who has heard about climate Fridays for Future? Everyone. So when did you hear about them first time? Do you remember?
Last week.
Last week. Cool. Anyone else, like a bit earlier? Maybe?
Months ago?
Like a year ago. Right. So actually this movement started in 2015. Already in 2015 there were already first global protests related to UN meetings on the climate change, but it got real momentum only last year with this amazing Swedish girl Greta Thunberg, who started protesting on her own, skipping schools on Fridays, and just she encouraged many people to join the movement, and now it is what it is right now. So this is a map of Fridays for Future and different events, and you can just check out also in real time what is happening. I think it's a bit outdated. There is even more happening right now. It's interactive. I encourage you to check it out. And Fridays for Future exists all across the globe, but just to give you an idea, what are their demands here in Germany? So they fall into two categories: long-term and short-term demands. On the long-term, by 2030, 2035, they are demanding that Germany should become carbon neutral, so have zero net greenhouse emissions. That means not adding up to the emissions in the atmosphere, should cease all the coal mining, and all the energy should come from the renewable sources. Till the end of this year, they are demanding that the government should cut all the subsidies for the fossil fuel, production and sources, shut 1/4 of the coal mines, and also introduce a CO2 tax. And they even came up with the concrete amount of the tax that they're proposing. Okay, that's it. Now we can move to the. I just want to say, give you guys some ideas about what you can do or what we can do on the individual level. Basically, this is the situation. Germany, as measured in 2014 and still valid right now, emits 11 tons of CO2 per capita per year. And if we want to stick to the Paris Agreement, we're aiming at 2 tons per year. So this is like a massive jump we're looking at. And if you guys are interested, you can calculate your own CO2 footprint. There are plenty of calculators online according to your own personal lifestyle. So this is an average footprint of an average German person, and here you can see it consists of the energy and heating sector, mobility, food, infrastructure, meaning hospitals, government, administrative buildings, like roads and so on, and other consumption sector. So let's look at the mobility sector first. Transportation in general is a huge contributor to the global energy-related CO2 emissions. It takes up 23%. And here we mean also direct emissions, but also indirect emissions through manufacturing, infrastructure, roads, and so on. And if you look at this plot here, it's showing, over time from 1970 up to now, the growth of CO2 emissions in the different means of transportation. And surprisingly, you will see that the main contributor is the road transportation, this blue area over here. So what do you think, which ways of traveling, individual traveling, leave the least carbon footprint? The most we probably can guess, it's the airplanes, right? What about the least?
walking and biking?
Huh?
Walking and
I
biking.
mean, a bit more like long distance.
Oh, okay.
Train.
Trains, yeah? Very good. So it is actually true, but you have to consider that the amount of emissions your transportation means produce depend on the distance and depend on the amount of passengers also. Like if you have a train, that is kind of pretty full, of course it's the most environmentally friendly way of traveling. But look, for example, if you have a small car and it is, packed, you have 4 passengers in the car, it can emit less than a bus, for example, in some circumstances. So there's something to consider. And there is this online application that you can use to, for a particular distance to calculate, compare plane, train, bus, car. So just for yourself if you're interested. So tourism. Of course, if we talk about individual transportation, we talk a lot about tourism. So tourism is a huge contributor to emissions nowadays. It's constantly and rapidly growing. So now it takes up to 8% of global emissions. And here we have a little plot where we can look at the residence-based emissions related to tourism. Like people, like you can see, the blue areas here are responsible for international tourism, and this is national tourism, the yellow level. So United States is number 1, and there is China, and then interesting, Germany is on the 3rd place. So German people do a lot of tourism and travel a lot. And 50% of the emissions caused by tourism are related to transportation. I mean, there are other types of emissions, but the 50% are transportation. So if we want, like with respect to travel, what can we do? There are different options, of course. An obvious one is we can travel less. If we still want to travel, we can fly less, drive less, and use transportation that are powered by the green energy. So then let's look at the consumption, and in particular shopping, because shopping, like the topic of shopping is also related to transportation. Almost half of the total transportation energy is the freight transport. Like for example, if you're ordering things online on Amazon and stuff, like the biggest impact is this last kilometers, when actually the delivery guy or woman are bringing your product that you purchased to your door. So this is the biggest, the road transportation is the biggest impact. So that's why it's important to consider buying stuff locally, where it doesn't have to, be transported. Also, we can think of, buying from environmentally friendly businesses, second-hand and long-lasting things, and repairing instead of buying. Interesting to look into, yeah?
I have a question for the shopping with the local. Is it, so do you know how much is the difference between going to a physical shop and buying something there versus shopping on Amazon and having it shipped to you?
It's
is
always,
it a lot, or is it?
I cannot, it's so many different factors. Like also your local shop, does it buy from local farmer, or is it transporting mango from South America? But all other things being equal, it's always better to go to the shop, like with your legs. So interesting is the IT sector, because this is now becoming like a huge contribution on the shopping side. Like the footprint of PCs, laptops, monitors, smartphones, tablets has been in 2017 estimated at 2.5% of the all global emissions, and it's super rapidly growing. So some estimating models suggest that it will be 14% by 2040. And here you can look, especially the worst contributors are smartphones and data centers. So the contribution of smartphones in 10 years, like projected to 2020, grew 735%. And it's still, the growing rate is still even growing. And data centers, of course, when you're using online services or computations on a cloud and stuff, this also has a huge contribution. Okay, food. Let's talk about food. What do you think? Which food products leave the most carbon footprint?
Meat.
Meat. Any maybe more specific? Beef. Perfect. Of course, beef, meat. Everybody heard about that. But here we can have a look at the CO2 emissions resulting from food. It's taking up a quarter of all global emissions. And animal products are more than a half of the food emissions. And from animal products, half of the emissions are produced by beef and lamb.
I have another question, how the numbers work. So we said that 8% of global emissions go to tourism, and
No,
then about half of tourism.
Yeah, that's a bit.
And half of tourism goes through transportation. So is this
food.
counted double, or is this?
No, like
so-
look, everything is so interconnected.
Exactly, so it's-
Food is in tourism as well.
Ah.
Of course, also food, also infrastructure,
Mhm.
also building hotels.
So are we counting some things twice then?
Yes,
Okay.
yes. So if you want to look at the, like this is the separation of different sectors, kind of.
Yeah.
Like here you have the percentages, and this is like an average German person, and average German person is emitting 11 tons.
Mhm.
So you can calculate the sectors, right? But yes, we're counting twice exactly, because it's really complicated to.
Yeah.
Right, so beef and lamb. But things are not so simple actually. It's super important how do you grow and sustain your cows. Because of course, yeah, cows is you have to feed them and you also need huge areas so for them to walk around. So it's like deforestation problem. Also, the waste produces methane, and you need lots of water also to grow them. So it's a huge, but look, this is a range of the amount of kilograms of emissions per serving for a particular food product. Like this is the low impact beef, which is like single farmer, just growing their cow, and this is the high impact beef where the cows are being brought on the deforested areas, and it's like a mass production. See how huge is this difference? And also interesting, like look at the chocolate. If you, for example, buy chocolate that was produced from beans that were grown in South America on the area that was before tropical forest and it was deforested, the emissions that this chocolate is producing are like more than the low impact beef in some contexts. And this is the vegetable protein, tofu. So interestingly, vegetable protein, no matter how it is grown, it's always producing less emissions than any animal product. So yeah, if you're interested, you can check out this paper and for your favorite food items, see. Another interesting topic is waste. Like when we're talking about waste, very often we're talking about plastic, right? But I want to draw your attention to the food waste, because actually waste takes up 5% of the global emissions, and the food waste is almost a half of all the waste emissions. So it's also interesting, like again, if we compare, if food wastage was a country, and if we compare it to other countries' emissions, so we can claim that it's will be emitting more than India, like the whole Indian country. And again, different food products have different impacts. Like let's look at meat. So this orange bars are showing the percentage of waste among overall waste, and the blue bars are showing a percentage of emissions produced by this type of waste. Like for example, this is meat here. So meat takes up a very small percentage of overall wastage. So not much meat is wasted. But since meat is so expensive in terms of emissions, the emissions from even this small amount of waste are still huge and are exceeding 20% of the total waste emissions. Like for example, look at vegetables and fruits. So they, especially vegetables and cereals also, they produce a lot of waste, like because usually vegetables they get bad very quickly, and obviously also there are a lot of related carbon emissions. So what can we do concerning with respect to the food? If we want to reduce our individual footprint, we can eat less meat, again buy local, consider carbon footprint of our diet, and definitely try to not waste too much food. Electricity and heating, 20% of the global, of the individual footprint. In general, electricity and heating is a huge sector. Globally, it takes up to 42% of global emissions. This is a screenshot for another interactive map that I personally find very cool, because in the real time you can look at the electricity production, consumption, and CO2 footprint for any chosen region. So here we have European region. And what do you think? Which energy sources produce the most emissions? Coal. Yeah. So yeah, this is from the same interactive map. So here you have Germany in 24 hours, and those is the different energy sources on the consumption side, and those are the corresponding emissions. Of course, you see coal massively outranks all the other sources, but also gas has an impact. So yeah, what can we do? If we can consider switching to the green energy, so-called Ökostrom. It's even not so complicated. Of course, consider saving air and energy, and if ever we own a house, we can insulate it. Think about the passive housing and install solar panels and so on. Also, investment is an interesting thing because not many people think about that. Like, okay, we are not, big companies with a lot of funds, but still, all of us we have savings. And where we put our money, where we put our savings can make a huge difference also in terms of emissions, surprisingly. Because we are giving our monies to like banks, or we're giving our money to pension funds, and what are they doing with them, it's worth investigating. Who has heard about carbon offsetting? Yeah? So what is carbon offsetting?
Like if you were flying a lot, then you might have, then the company might be like, oh, buy carbon offsetting to reduce your emissions from this flight, but I don't know how legitimate it really is.
Right. So yeah, carbon offsetting is a financial contribution to the projects that are offsetting emissions made elsewhere, exactly like you were describing. So typical projects happen in the developing countries actually, and they are typically related to planting trees, supporting renewable energies, collecting methane, or installing some more energy efficient, light bulbs or stoves and so on. This is a very choosing a carbon offsetting project is really not easy. You have to consider many factors. Like some of them I'm just listing here to give you an idea. So one important question, how do you evaluate the impact of the project? How can you decide after a certain amount of years that the project was successful? What are the other side effects and of the projects outside of its boundary? For example, if it's a afforestation project, do they maybe remove indigenous people from certain areas to plant trees? Maybe they introduce invasive species of plants. All of those things are something to consider. Also, does the project permanently reduce emissions or not? Like if you're, for example, paying for afforestation and then these trees were going to be chopped in a few years for firewood, it doesn't make much sense. Something to consider. Other additional benefits. Again, like afforestation project which restores ecosystem has additional benefits. So this is like a plus to consider this project. So there is a certification quality standard called Quality Assurance Standard. It's an international standard that you can look at, and they give certification to those projects. So so you see there are so many different options you can consider individually, how to shape and manage your lifestyle. And there is an interesting interesting article comparing 5 fictional characters and their different lifestyles according to emissions. And you can see actually that for at least for 3 characters, it's fairly possible without being miserable to reduce the carbon footprint quite significantly. But it's interesting to look at this person here. Like the fictional character Katharina, who is totally ascetic and living a very, very simple lifestyle. So she managed to reduce her carbon footprint only to 5 tons per year. And remember, our aim was 2 tons per year, right? So it's still not enough. And what it's teaching us is that in an industrial country like Germany, we cannot individually reach the goal of the Paris Agreement just on our own. So that's why activism is another way to contribute in a very significant way. Again, participating in protests, voting for conscious politicians, influence your organization where you study or work, and of course educating people around you. Yeah, what we're trying to do right now. And on this note, I guess you guys know, but if you don't, there will be 2 global strikes coming up, and in October also we, along with other organizers, we're organizing a climathon here in Heidelberg, which is a hackathon focusing on climate issues, and it's like all about your creativity to come up with solutions for this local area here, and you're all welcome. And just to wrap up, like the climate change watches, like our watches clocks are ticking, but as Jan was pointing out there is still like carbon budget left, so there is still time, and the point is that we cannot go on like none of us like we've been going on so far. Changes need to be done on a global level, on a specific country level, on organization level, and on our individual level, and we have to be really inventive and creative about it, because there are so many different ways we can make things better. That's it.